All right. So shall we begin?
Yes, sir.
Okay.
Yes,
The number of students seem to be less. It's like 28. Uh, can I wait for a couple of minutes to let others join as well?
Yes, sir, we should wait for 5 minutes. Let other join.
A couple of minutes, yeah. And today is my last lecture for this course. Okay. And next week is going to be study holidays for you guys. Okay. And you might end up having me again in your third semester, possibly, for your physics of semiconductor devices, for CS, or for physics of engineering materials for ME, mechanical. Okay. So, yeah. It doesn't seem to be increasing at all. So it just stays at 30. I'll rather begin, okay? I don't think more people are joining today.
So, sir, like
Yeah.
on Thursday and Friday, like today, tomorrow, and the day after tomorrow, you have class. So you will not take the classes.
No. As I told you guys, I'll be leaving station. I'll be out of station for a couple of days, for about a week. So I'll be leaving. So there won't be any classes. Okay. All right. All right. So let's go directly jump into Maxwell's equations. Have you guys heard of this set of equations, Maxwell's equations, before?
Yes, sir.
Yes.
Okay, so you know that there are 4 equations in Maxwell's equations, right?
Yes,
Yes,
sir.
sir.
Yes.
Okay, good. So have you guys come across dive, curl, and all that, and grad, and Laplacian, and all that? Have you guys come across these symbols in mathematics?
Yes, sir.
No.
We are started.
Yes, sir. We were
Yes.
introduced to them.
Okay, you are introduced. You have
We have
been
done.
introduced to this. Okay. All right. So we are going to need that. Of course, I will explain a little bit about what equation means, but you need to be comfortable dealing with these vector operators. Okay. All right. So let's begin. So in late 18th century, Maxwell collected what was already known about electrical and magnetic phenomena together into a set of equations. Okay. And the first equation was Gauss' law. Okay, Gauss's law. And that is, hold on. Divergence of E is rho over epsilon naught. Okay, there are 2 forms for each law. Okay, this is the differential form. There is also an integral form. Okay, the integral form would say E dot ds is dv.
Q over E naught.
Q by epsilon.
1 by epsilon naught. Yeah. Okay. So this is over surface. This is over volume. Okay. You guys know these Stokes theorem and Green's theorems and all that. Green's theorem and all that. Have you been introduced?
it was supposed to be, we should learn today itself, but we didn't learn it till now.
Okay. Okay, so I don't want to get in there, but I will just give you guys the physical interpretation of what this equation is. Okay, what this equation means. All right, so integral rho dV is just Q, right? It's a total charge within that volume. Am I right?
Yes, sir.
Okay, and what is E dot ds? ds is the, so if you have a surface, some surface, and ds is some surface element, okay, with a vector along a perpendicular direction to the surface, right? And then if you have some charge here, let's say this is a charge in the center, some Q, okay, you will have field, electric field coming out like that. Am I right?
Yes, sir.
Am I right? Okay.
Yes,
So
sir.
what you do is what the Gauss's law says is that the amount of electric field coming out of this, if you draw any surface around some charge, you draw some surface, any surface, it can be bent, curved, whatever, doesn't matter. It doesn't have to be circular. Draw any surface and do this thing. Take the electric field vector at that point, dot it with the volume element, surface element, and integrate over the entire surface. Okay, if you do that, that will give you Q over epsilon naught. That will give you the total charge. That will be proportional to the total charge inside. That is what Gauss's law says. Does it make sense?
Yes, sir.
Okay,
Yes.
so basically the amount of charge inside is proportional to the electric field that comes out of this the electric field inside the volume. The charge inside the volume is proportional to the electric field that comes out of the surface encompassing that volume. Am I clear?
Yes, sir.
Okay, so the more the charge inside, the larger the electric field is. Am I right? Yeah, that is obvious, right? So if you just
Sir.
integrate, yeah.
Sir, why it is called Maxwell's equation and not Gauss's equation?
Maxwell just put those four, there are four laws, and they are put together by Maxwell, even though individually they are called by different names. When they are put together like this, they are called Maxwell's law, Maxwell's equations. But individually they are called by different names. Okay. So Gauss's law is just one of the Maxwell's equations, because Maxwell just collated them together. Previously, they were just independent. People thought that Gauss's law had nothing to do with Faraday's law, let's say. They didn't know the connection. They didn't figure out the connection between these different laws. Only after Maxwell put them together that people realized that they were all connected. Okay, and that's the reason they are called Maxwell's equations. Okay. Okay, so so basically, what the Gauss's law says is that if you have a certain amount of charge, the electric field that goes out, that is proportional. How much electric field goes out from the charge is proportional to the charge inside. Okay, now how do you measure how much electric field is going outside? One way is to dot it with the surface element and take the electric field vector, dot it with the surface element, and integrate over. Okay, but there is also another way. Okay, you can just go to a you have an electric field. So you have a field of vectors. Okay, at different points you have different electric field vectors, right? You have a charge here, let's say. Okay, the electric field goes down as you go far away from the charge, obviously. Okay, all right. Now you can see that the electric field vectors are diverging. They are going out from the center. All of the electric field vectors are pointing out from the center, right? Am I right?
Yes.
Yes, sir.
So how much an electric field goes out from a point is measured by divergence, div E. This tells you how much the electric field is diverging from a point. If you measure divergence of E at this point, it'll be very large. If you measure the divergence of point at this point, what would you think? What do you think we'll get?
So the divergence at the charge should be less, no? Because the electric fields are very near to each other. The electric field lines are very near. So at the
No,
point where the charge is,
how they are diverging. The electric fields are diverging. They are moving out. See, they're spreading out. You understand the meaning of the word divergence, right? How things are diverging. What is if there is a greater angle between these E vectors, right? Whereas if you go far away, the angle becomes smaller. They are diverging. Do you
okay,
understand
sir,
that?
got it.
Okay. Now, what about this element here? For this element, the divergence of the electric fields is very high. For this element, what is the divergence?
It will be lesser than the center.
Okay. Do you want to do this E dot ds for this particular cube here? And if you do that, what do you think you would get? There are some electric fields going in and there are some electric fields coming out, right? You will find out the amount of electric field that goes in and the amount of electric field that comes out of that volume is the same. So the net integral is 0. So the divergence is 0. The electric field is not diverging from here. Some amount is going in and some amount is coming out. They are exactly the same. The amount that goes in, the amount that comes out, they are the same. So the divergence is 0. There is no divergence. If there is a divergence, what you would see is electric fields coming out, electric fields coming out like this, everywhere. They are coming out everywhere. The amount that goes in would be much smaller than the amount that comes out. That is when you... Here, there is no divergence. It's just flowing in and flowing out. The same amount is flowing out. Electric field is not created inside. So the divergence would be 0 there. Does it make sense?
Like, does divergence mean like flux?
It's the total amount that goes into a particular volume and the total amount that comes out of the particular volume. It is not flux. If it is flux, then if you have a surface, you have a lot of electric field vectors. That is a flux of electric field vectors. But we're not calculating flux. We are calculating the change in flux at a particular point in time, a point in space. Is the flux created there inside? No. Here, at this point, the flux is created. There is flux coming out of this surface in all directions. Electric field lines are coming out. Here, the total electric field lines are the resultant electric field lines, meaning the ones that are coming out minus the ones that are going in, is 0. The number of electric fields lines that go in equals number of electric field lines that come out in this surface here. So the divergence.
So then that means the charge density is also 0 over there.
Exactly. That is why the divergence is 0.
So I'm getting a little bit confused. Charge density has no relations with the electric field density because there is some electric field there. So if the charge...
But divergence of electric field is directly related to charge. It is proportional to charge. It is equal to rho over epsilon naught. How much electric field diverges is related to a charge. Gauss law actually connects electric field and rho and charge density.
But like in Gauss law, that we say that integral E vector or dA vector is equal to charge enclosed upon epsilon naught. So that means a charge which is enclosed in a closed surface, only that charge is considered. Whatever charges are outside the closed surface, they are integral E vector dot dA vector is 0 because there is electric field going inside the solid and it is also coming out. That's why it is 0. So
Exactly.
same thing here.
Exactly. Yes, exactly. Beautiful. That is exactly right. Okay, only when you create a volume, when you create a surface enclosing a volume, if there is a charge inside that volume, you will have electric field vectors coming out of that surface. Then you will have some divergence. The electric fields are diverging from that point. Okay, if there is no charge inside that volume, then the amount of electric field vectors going in equals the amount of electric field vectors coming out. So there is no divergence. Divergence means how much electric field vectors are created at that particular point. If the number of electric field vectors going in and coming out are the same, there is no divergence. Okay, so divergence is proportional to the charge density. Do you understand that equation now?
So how are we going to
Yes,
measure the
sir.
divergence? I mean, is it going to be measured in terms of the angle between the electric field lines?
No. So basically, you're going to measure divergence just mathematically. This is a definition. Dive E is I dou by dou x Ex plus J dou by dou y Ey plus K dou by dou z Ez. This is exactly how you're measuring divergence. Oh, sorry, there is no E. Sorry. I'm sorry. There is no IJK. Okay, it's dou Ex by dou x plus dou Ey by dou y plus dou Ez by dou z. That's it. That is how you measure divergence. How much Ex change along x direction, how much Ey changes along y direction, how much Ez changes along z direction.
So the electric field exists in that region, and so if we solve it, that del Ex upon del x, and we solve this complete equation, it will come out to be zero. The terms will cancel each other. Is there something like that?
Yes. The electric field in the so let's it's easier to do it in the integral form. Okay, EDS equals Q over epsilon naught. Okay, so let's say if you let's say you take a surface. This is our surface. Okay, let's say you take a surface. Okay, there is no charge inside. All right. So if there is no charge inside, if there is a charge outside somewhere, then electric fields are coming in like that. Okay, and electric fields going out like that. Okay, and if you do this integration, you will find that it is zero over this surface because it is not enclosing any charge. Okay, so what does that mean is that if you calculate dou Ex by dou x at every point in the space and average over that, that'll be zero. The rate of change in space, the rate of change of Ex averaged over the entire space here is zero. Or in other words, divergence of E d tau, this is over volume. There are triple integral. This is over volume. This is equal to surface integral E dot ds. This is the divergence theorem. Okay, this is divergence theorem, by the way. So this is the same as this. So when you do this, you're basically doing dou Ex by dou x, calculating the dou Ex by dou x at every point in this volume, and you're integrating over that. Okay, and that will be zero. Not just dou Ex by dou x, you have to do all three of them. If this is not zero, if this is some constant, then you will see that this becomes another constant that completely vanishes, completely annihilates the x constant. X. If this is non-zero, then something else is going to be going to have an opposite value, which makes it zero. In total, in sum, they will always be zero. Okay.
Yes, sir.
Yes.
It takes a bit of getting used to to understand what a divergence means. It requires some getting used to. Okay. It basically measures, divergence is a very good name. It measures how much the vectors are diverging. Okay, this field, let's say you have a field where electric field vectors are like that. Is this electric field diverging? Is there
sir.
any divergence inside this electric field?
No, sir.
No,
No,
because
sir,
this is
there
constant.
is
The
something
amount that
out.
goes in, yeah, it's a constant. So there is no divergence. The field is constant. If you do dou EX by dou X,
Sometimes
I'm sorry?
it depends on radial distance also. So it is diverging then.
Yeah. Let me draw that again. Okay. So let's say you have a charge. Okay. You have electric field, high electric field here, right next to the charge, right? And then as you go farther, your electric field is reduced, right? Am I right? Okay. And you go a little farther, your electric field becomes even smaller. Am I right? It goes as 1 over r square. The electric field is 1 over r square, right? It goes as 1 over r square. Am I right?
Yes, sir.
Now, if you draw a surface here, you will see that some vectors have this direction and some vectors have this direction. Okay, some vectors have this direction and some vectors have this direction. They all cancel off.
Yes, sir.
If you integrate over the directions, they all will cancel off eventually. You will find that they will cancel off. The amount of flux that is coming into the surface and the amount of flux that goes out of the surface will always be same. If there is no charge inside. Only if there is a charge inside, there is no flux coming in, but only flux going out. So you have non-zero divergence. Okay, divergence just basically measures how much flux comes in minus how much flux that goes out into a
So,
surface.
sir, basically, divergence is the net flux passing through a surface.
And net flux coming out of the surface. Passing through the surface is a different one. Here, if you have this kind of a situation, there is a net flux passing through the surface, but divergence is zero. There is some flux passing through the surface. Okay, but the divergence is zero because there is no new flux created from within the surface. The flux that's coming here in equals the flux going out. So there is no flux being created. Here, in this surface, there is flux created. There is no flux going in, only flux coming out. So flux is being created, and that flux is being created by the charge.
So that means divergence will only be obtained when we have a charge enclosed within that Gaussian surface.
Exactly. And that is exactly the equation says. Divergence of E equals rho over epsilon naught. When there is divergence, there is a charge inside. When there is no charge inside, there is no divergence. The flux goes in and the same flux comes out. Does it make sense?
Yes.
Yes,
Okay.
sir.
So this is Gauss' law. This people already knew, in the 1600s. Even in 1600s, people knew this. Okay, 400 years ago. All right. So that is number one of Maxwell's equation. Number two, divergence of B is zero. This is Gauss's magnetic law for magnetism. Okay. What does it say? It says that B cannot diverge. There is no divergence for B. How is that possible? Let's say you take a magnet. You take a magnet.
Two poles are always,
I'm sorry?
North Pole and South Pole are always together.
Yes. Okay. You're getting somewhere. Yes. You're getting somewhere. Exactly. So let's take a north and south pole. So if you draw a magnetic field, it'll go like that, right? Right?
Yes.
Okay.
Yes,
It'll
sir.
go like that. Is there any starting point for these lines? Do the lines start somewhere?
No, sir.
Okay. So
Yeah,
wherever you
no.
draw a surface, if you draw a surface here, or if you draw a surface encompassing the magnet, the number of flux lines that goes in equals the number of flux lines that comes out. Am I right?
Yes.
The flux lines are not being created anywhere. Am I right?
Yes, sir.
Okay, so divergence of B will always be zero. Flux lines are not created anywhere. In charge, when you have a charge Q, you have flux lines created. The flux lines are created, whereas here, the flux lines are not created. Can you guys tell me why? Why are flux lines not created anywhere? What is the difference between a charge and a magnet?
So magnetic monopoles don't exist, charge monopoles exist.
Very good, very good. So this is a charge, this is a monopole. Okay, this is a
And
monopole.
about the electric and magnetic field lines that one cross each other and one forms a closed circle and another don't form a closed circle due to that thing.
Yeah, I'm coming to that point. I'm coming to that point. Okay, so Q is a monopole, whereas a plus Q and a minus Q, if you put them together, this is a dipole. Okay, so whatever starts here ends here, right? Am I right?
Yes, sir.
Yes, sir.
So what about divergence for this surface? If I draw a surface around plus Q and minus Q, what is the divergence?
0.
Yeah, the
So
divergence is
zero.
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 Divergence is zero, right? Because the total
0.
charge is zero. Plus Q and minus Q is zero. So the total charge is zero, the divergence is zero. It's exactly the similar situation here because we are making a dipole. This is a dipole. N and S, this is a dipole. This is a magnetic dipole. Okay? If magnetic monopoles existed, then you would have something similar to Gauss's law for electric field, for electric charges. But there are no magnetic monopoles. Okay? So since we are dealing with dipole, divergence of B will always be zero. Unlike charge, in the case of charge, you have monopoles, whereas in the case of magnetism, there are no monopoles. Okay, so this basically statement says that there are no magnetic monopoles. Basically, no magnetic monopoles. Okay, does it make sense?
Yes, sir.
Yes.
Okay. Okay. So by the way, nobody knows why there are no magnetic monopoles. Okay, it's perfectly allowed by physics. Okay, but we don't find them at all. Okay, now the third law is Faraday's law. Okay, so Faraday's law says curl of E equals minus dou B by dou T. Okay, what does this say is that so let's take this kind of a loop. Okay, a wire loop. This is a wire. This is a wire loop. Okay, and you're attaching a voltmeter to this two ends. You're taking the two ends and attaching that to a voltmeter. And what you do is you take a magnet, NASA, and you move it through this loop. What do you think would happen?
Sir, potential difference induced on a
Okay, you will see a potential
coil.
difference. Why is that?
Sir, because air
Due to the
magnetic
change in
field
flux.
changes which create a non-conservative and creates electric field.
It creates an electric field, yes. So what creates an electric field? Magnetic
Sir,
field creates an
changing
electric
magnetic
field.
field.
The changing
No, sir,
magnetic
changing
field.
flux of change in
Ex-
magnetic field.
Exactly. The changing magnetic field creates an electric field. Okay. And when you move it, when you move through this, the amount of flux that comes out through this, that goes through this wire changes, right? And that flux change creates an electric field around the wire, right? Right? So basically d phi by dt, this is the flux, phi is the flux, okay? Phi is integral b dot ds. Okay, ds, this is the surface, this is surface, this surface, the surface encompassed by this loop, wire loop, okay? And phi, the flux, is integral over b dot ds. It's okay, right? You guys understand that part, right? That is the definition of flux, right?
Yes.
Okay, so the flux changes, and this change of flux is proportional to the voltage, right? Okay.
Yes.
So what it does basically, when you change the flux, the electrons in the wire gets pushed like this in a specific direction, right? They are pushed in a direction perpendicular to the rate of perpendicular to the flux. Am I right?
Yes, sir.
Okay, so it is as if there is an electric field acting on these electrons. The electric field. So if the flux is going this way, then this is perpendicular. This surface is perpendicular to this flux lines. This is magnetic flux lines. This is B flux lines, and the electric field is in this direction, in the direction perpendicular to the flux lines, magnetic flux lines, right? Am I right? So
Yes.
basically the electrons would go round and round and round like this. Okay. Okay, when you change the flux, the electrons are going to, that's basically your electric motor, right? Generator, electric generator. That's what the generator does. Right? What does a generator, electric generator do? It moves the magnets, and the magnetic flux changes, and that change in the magnetic flux creates an electric voltage across coils wrapped around the magnets. This is exactly what is going on in the generator, right? Okay, so basically when a magnetic field changes in time, dou b by dou t, there is an electric field that is created which circles the loop around the magnetic field. Okay, it's a circle. It goes circle. It curls around. You know what a curling means, right? You understand the meaning of curl, the word curl?
Yes.
Because you have come across the word curl, like a cat curled on the carpet. Or the game, yeah? And there is a game called curling also in Olympics. Have you guys seen that game?
Yes, sir.
Curling?
Yes.
Yeah. So basically it's a spinning ball. It's not a ball, it's a heavy weight on ice. Okay, and that spins. Okay, so curling means to circulate. It is to circulate around a loop. Okay, so when you say the electric field curls, you should be able to measure how much it curls. Okay, and that is given by this quantity, R integral E dot dl. This quantity, this is over the wire, the circle wire. It's over a circle. Okay, you take the electric field at every point, you integrate it by dotting it with a dl element, which is the element that points in the direction of the wire. Okay, dot it with that element, and then integrate over that. You will get the curl, and this are the same thing. They are equal. Curl integral curl E over surface ds dot ds equals integral E dot dl. This is over length. This is over this is over the wire of the circle. Okay, this is called Green's theorem. You guys have read this? Have you guys come across this theorem already or no?
No, sir.
Not yet.
No, sir.
Okay. Anyway, it's not exactly needed, but if you take the electric field at every point on the wire, the electric field is pointing along the direction of the wire, and you dot it with the dl, which is the element of small element on the wire, length element on the wire, dot with that and integrate over the entire loop of the wire. You get how much you get the idea of how much electric field is circulating. That's very meaningful, right? It's very intuitive, right? Is it intuitive or no?
Sir, what is the significance of the LHS expression?
Significance of what?
This one, curl
The curl?
cross. Yes, this one. What is the significance of this?
The significance is, see, if there is no electric field, there is no magnetic field, changing magnetic field inside the loop, wire loop. What is the curl? How would there be electric field going around the circle? The significance is here we are measuring how much the electric field is curling, how much the electric field is circulating around the wire. That's what we're trying to do.
Oh, okay, sir. Okay, sir.
Okay, we're trying to measure how much the electric field is circulating in the wire. It's curling around in the wire. How much it is. So let's say you have an electric field that goes like this. What is the curl of that electric field, of this electric field? It's non-zero. Okay, because it's going around in a circle like that. It's curling. Okay, let's say you take an electric field like that. What is the curl of this electric field?
Zero.
Zero, exactly. Very good. It's zero. Okay, so this is diverging electric field. That is not curling at all. Whereas this one is curling. Okay, curl of this field is non-zero. Curl of this field is non-zero. Okay, so you have an intuitive idea of what a curl means. Curl means how it is circulating, how the vector field is circulating. Is it going
So
around?
we have studied something called eddy currents. So we have studied something called eddy currents. Is it
Yes.
something like that?
What we are talking about is much more abstract than eddy currents. Eddy currents can be quantified in terms of curl. Okay, so if you have an eddy current, let's say you have a material, and currents are going like this. Okay, the electrons are going around in circles like that. Okay, so you can say that there is a current J of x comma y. The current J is a function of position, right? At this point there is certain current. At this point there is a certain amount of current. At this point there is a certain amount of current. Am I right? At each point you can define the current, right? Am I right?
Yes, sir.
Yes, sir.
So now
Yes.
you can calculate curl of J x comma y. Okay, you can calculate this. This will give you how much eddy current is there, because eddy current is just circulating current. This will tell you how much the current is circulating, and this will quantify how much of that current is eddy current, because eddy current is a circulating current. How much the current is circulating. This isolates the circulating current and leaves out the current that goes in and comes out. The current that diverges or something. It leaves out all the rest of the other current. It only takes into account the circulating current. It quantifies the circulation. Do you understand that? The
Yes, sir.
curl is an operator on a vector field. This is a vector field. Okay, a vector field is a vector. There is a vector at every point in space, x comma y. At every point in space, you associate a vector. Okay, and that is a vector field. And this curl operator operates on the vector field, and it gives you some number, some vector. Okay. Okay, it measures how much the field is curling around. Okay, another example. You have a faucet hole, like water faucet hole with lots of small holes inside, and water pours in from a pipe faucet. Okay, and the water goes in like that. The water flows in like that, right? The water never flows in directly. It just circulates around. Am I right? Am I right?
Yes, sir.
Yes.
Yes.
Okay. Now you can measure the velocity of the water at every point x comma y within this surface. At every point, the water has a velocity v, right? Yeah. Now, if you
Yes.
want to measure how much this water is circulating around, then you can just say curl of v x comma y. This will tell you how much the water is circulating. Okay. Instead, in a case where you have the same faucet, but water there is very little water and the water flows right into the hole. Okay. In this case, if you measure curl of V, what would you get?
So
If the water,
zero.
zero, you would get zero. Here the water is circulating around and getting into the hole. Here the water is flowing directly into the hole. There is no circulation, and then you will get a zero. Okay, so basically curl gives you an idea of how much circulation there is. Does it make sense? Does it make sense?
Yes, sir.
Yes,
Okay.
yes, sir.
If there is any question, do let me know. Okay, so basically curl of E is how much the electric field curls around the wire as you move the magnet through the wire. So if this is a magnet and this is a wire, if you move the magnet through the wire, there's going to be an electric field set up, and the electrons are going to move around the wire. The wire gets heated up. Okay, so basically this electric field, how much the electric field circulates, is proportional to the change of flux through that surface. Or you take the surface, you calculate the flux through the surface and make the rate of change, take the rate of change, and this curl would be proportional to that. That's Faraday's law, right? You guys have studied this, right?
Yes, sir.
So what we're doing is just giving an equation to simulate Faraday's law. This equation basically explains everything about Faraday's law. Okay. Now its curl E is minus dou B by dou T. What is this E? Minus means? You guys have studied that.
Sir, Lenz's law. Sir.
Sir,
Exactly.
it indicates in the opposite direction to the change.
Yes.
Like
Yes.
the
Then
magnetic field through a coil changes
It
with
opposes
answer
the
to
change.
try to oppose it. So
Yes,
since it's opposing, by putting the negatives.
Exactly. So that negative sign is a Lenz law. Yeah. So you guys know that. Okay. So basically, let me state it again. If you're trying to change the magnetic flux within this loop, the electric field would be set up in such a way as to create another magnetic field that opposes the rate of change of the magnetic flux. Okay, that is what this negative means. Okay, and basically this negative sign, there is a lot of technological relevance to this negative sign. The whole high-speed trains, high-speed levitating trains, like in Japan and China, these trains basically fly, I mean literally fly, because of this negative sign. Okay, because on the tracks are magnetized. Okay, and you have the wheel, and the wheel as it moves through, there is a magnetic flux that comes through. Okay, and then there is a small eddy current that gets created, and those eddy currents create another magnetic field which opposes the track, and the wheel gets lifted up. Okay. All right. So basically, the levitating trains, the basis of levitating trains is that negative sign, the Lenz law. Okay. All right. So you guys have an idea of this Faraday's law, right? Now. Okay.
Yes,
Rate of change of magnetic field creates a curling electric field. That's all it says. Okay. And the fourth law, so that's the third one. The fourth law is Ampere's law. Okay. Here it's opposite. There, before this, we saw a changing magnetic field created a circulating electric field. Now we will see a changing electric field creates a circulating magnetic field. Okay. Let's say you have a wire, okay, which carries a current I or J or whatever. Okay. The current flows through this. How is the magnetic field look? How does the magnetic field look for this wire?
Circle.
That's curling.
It's a circle. It's curling. It's curling. Exactly. So basically, curl of magnetic B is proportional to I. Right? If there is no current, there is no magnetic field. And the higher the current, higher the curling. Simple, right?
Yes.
Okay. Now let me introduce a small wrinkle here. Okay. What I do is let's make a capacitor out of that. Basically, we interrupt this and make a capacitor out of that. Okay. Now, will there be a magnetic field in this region, in the region between the two plates? Will there be a magnetic field?
Yes, sir.
There will be a magnetic field, right?
Yes, sir.
Sir,
During
there is no-
charging, if you use DC.
Yeah, if there is charging, of course, if it is charging, there is a magnetic field at the center in between these plates, right? And where is that magnetic field comes from? Does it come from current?
So from the
Yes, sir.
changing electric field.
Very good. From the changing electric field. So it is not just the current, but this is also proportional to changing electric field.
Electric field. Yes.
Okay, so it's basically we're going to write the Ampere's law as curl of B equals mu naught J plus mu naught epsilon naught dou E by dou T. Okay, so this term is introduced by Maxwell. This is Maxwell's term. Before Maxwell, nobody knew this. Okay, Maxwell introduced this term to make it symmetric, make the equations symmetric. Okay, this people knew already. Okay, when you pass the current, this is current density, by the way. Current density. Okay, so when you pass current, there is a curling magnetic field around that wire. People knew that, but they did not know that changing electric field also creates a curling magnetic field.
Maxwell's term come for displacement current.
Yes, this is displacement current. Exactly, this is displacement current precisely. Okay, this is called displacement current. It's an unfortunate term. It doesn't mean anything. The displacement, that's why I avoided using that, because the displacement current doesn't mean anything. Okay, he imagined that to be some kind of current, but you know, it's not.
Sir, what is actually?
I'm sorry.
What is actually displacement current? Why it is called displacement current?
Yeah, it's an unfortunate term. As I said, it was just Maxwell's term. It was an unfortunate. There is no current there. It is just a changing electric field. The electric field is changing, and the changing electric field creates a magnetic field. That's it. That is the whole idea behind displacement current term. But the term itself is useless, meaning it means nothing. There is no displacement of anything, and it's not a current. Okay, it was an unfortunate term. Okay, so you would just call it Maxwell's term. That's it. Don't worry about the displacement current. It just stuck. It's like an old term that is stuck. That's it. Okay. So far, so good.
Yes.
Yes.
Okay. So now let's go to Maxwell's wave equation. Okay, Maxwell's wave equation. So let's go into a space where rho is 0, meaning that there are no charges, and J is 0. There are no currents. No charges, no currents. Okay, and let's write down the equation, Maxwell's equation, in this case, in the special case of rho, no charges, no currents. All right. Okay, now, so this is for the special case of no charges, no currents. Okay, the first is divergence of E is 0, no charges, right? Second is divergence of B is 0, which we already know, no monopoles, no magnetic monopoles. Okay, third, curl of E is minus dou B by dou T. Okay, changing magnetic field creates curling electric field, and curling magnetic field is related to plus mu naught epsilon naught dou E over dou T. Okay, changing electric field creates curling magnetic field. Okay, so you see the symmetry between these two terms, right? Changing magnetic field creates a curling electric field. Changing electric field creates a curling magnetic field, right? This is where Maxwell came in onto his own. Basically, these equations are pretty much known except for this term. Okay, this term Maxwell introduced, but everything else was known already. Okay, people measured this mu naught and epsilon naught and all that, and these were very static measurements. Mu naught and epsilon naught, they were measured using cotton and paper, those kind of experiments. Okay, experiments were really static experiments. Okay, and Maxwell looked at this equation and he thought there seems to be pretty good symmetry there. So let's explore further, and he did. What he did was to apply curl on this. So curl E. Okay, this is just mathematics, by the way. Curl E is grad div E minus del square E. Yeah, I'm sorry.
Vector triple product formula that will be here applied.
I'm sorry, what formula?
Vector triple product formula, A cross B cross C.
Exactly, vector triple product. So you guys have learned this, right?
No, we have
Yes,
learned
sir.
only
Yes, sir.
Yes.
formula, but
Okay, yeah, okay. So it's
with
curl.
the rule, but this form.
Yeah, curl equals grad div minus del square. That is Laplacian. Okay, this is the rule. Okay, so you know the divergence V is 0, so this term goes away. Okay, so basically the third equation gives you minus del square E equals minus dou B by dou T. Okay, similarly, if you do this for the second equation, what you would get is del square B equals, hold on. Oh, sorry. I made a mistake here. This is curl B. I applied a curl on this side. I forgot to apply curl on this side. Right? Am I right?
yes, sir.
Yeah, okay. So here it's curl of okay, mu naught epsilon naught dou E by dou T. Right? Okay, what is curl B now? So minus del square E equals, curl B is mu naught epsilon naught dou square E by dou T square, right? Curl B is mu naught epsilon naught dou E by dou T. Am I right? It was just Maxwell's third equation. Okay.
Yes, sir.
So curl of B, Laplacian B is same as previous one, dou square B by dou T. Okay. Now you basically separated.
So what is Laplacian?
Laplacian is just del square is dou square by dou x square plus dou square by dou y square plus dou square by dou z square. That is the Laplacian. It is del dot del. Okay, where del is I dou by dou x plus j dou by dou y plus k dou by dou z. And when you say del dot del, you get this. Okay. Sorry, I forgot to explain that to you guys. Okay, del square is just this expression. It's an operator. It's a Laplacian operator.
It's a dot product of delta operator.
Yeah, delta dot delta.
Yes, sir.
Okay. So look at these set of equations. You have an equation for E and an equation for B. They're separated. They're not coupled anymore. But now it is second order. Earlier, in Maxwell's equation, the E and B were coupled and they were first order equations. Now the equations are second order. It's dou square by dou x square. It's a second order equation, but they are decoupled. Okay. Now how do they look like? You guys know a wave equation. We've talked about it. Dou square U by dou x square is proportional to dou square U by dou t square. We've talked about this, right?
Yes, sir.
Yeah. So look at these equations here. How do they look like? This del square is dou square by dou x square in, let's say, in one dimension. Forget about y and z then. Then this looks just like that, just like the wave equation, right? Am I right? Yes or no?
No, sir, we are not getting it. I am not getting it.
Okay.
Like
So
how
del square dou square by dou x square, dou square by plus dou square by dou y square plus dou square by dou z square. Okay, so del square E is dou square E by dou x square plus dou square E by dou y square plus dou square E by dou z square, right?
Components Ex, Ey, Ez.
No, this is it's not a vector operator now. It's just a single operator. You have to differentiate everything with dou square by dou x square. You have to generate dou square by dou x square Ex plus Ey plus Jey plus Kez. You have to do that. Plus dou square by dou y Iex plus Jey plus Kez. You have to differentiate every term with every x and y and z. Okay, we're not dotting here. Okay, this is a scale. This is like a scalar operator. This is not a vector operator. It's a scalar operator. Okay.
Yes, sir.
Okay. Okay. All right. So let's imagine that E is independent of y and z. Let's just one dimension. Let's think of one dimension. Let's ignore this. Okay. Let's just ignore that. So you will have dou square by dou x square equals mu naught epsilon naught dou square E by dou t square. Right.
Yes, sir.
Right. So does this look like a wave equation to you guys?
Yes, sir. Here we also got the velocity of wave, electromagnetic
Exactly.
wave.
So it's 1 over c square is mu naught epsilon naught. And you can just say c equals 1 over square root of mu naught epsilon naught. And Maxwell already knew the values. Even then, even in the late 18th century, people knew the values. And he plugged it in. He got 3 × 10⁸ meters per second. Bingo. He knew he was onto something. Once he got the value, he knew that the light waves and radio waves were electromagnetic waves right away. It was a big revelation. Okay, epsilon and mu naught were measured using like simple instruments, simple static instruments. They had nothing to do with light. They had nothing to do with electromagnetic waves. But when you just plug them together in this exact form, you get the wave equation. You get the velocity, wave velocity of light. It's amazing. It was a big revelation. Right? He must have been ecstatic. Right?
Yes, sir.
Okay.
Yes.
Okay. So what is going on here is okay. Before we turn to other things, we can imagine. Let's imagine how the wave looks like. Let's try to work out how the electromagnetic wave looks like. Okay. For that, we have to simplify the problem. Let us imagine the electromagnetic wave is going in the z direction, only in the z direction. It's not moving in any direction, just along z direction. Okay, and along x and y direction, the wave is a constant. Okay, so the wave is infinite along x and y. What does that mean is that if there is an electric field here, some electric field vector E naught somewhere here, after 10 kilometers, the same electric field vector 10 kilometers along x direction, okay, there is the same electric field vector E naught, and along y direction, the same electric field vector E naught. Okay, the vector, the electric field and the magnetic field does not change along x and y. Do you understand that?
Yes, sir.
Okay, so basically, the electric field E is only a function of z, and it's not a function of x and y. The same with B. B is only a function of z, and it's not a function of x and y. They are constants along x and y. Okay, it's an assumption that we make to simplify understanding the equation. We are just simplifying it by taking it to be constant along all directions except z. Does that make sense? We still don't know the E and B are which direction E and B are pointing. We don't know that. We just know that E changes along Z. E is varying along Z, but we don't know the direction of E. It can as well be pointing in Z direction, X direction, Y direction. We don't know. Okay, it is a function of E. It does not mean that E is just EZ. E is not equal to EZ. Okay, this is Z component of E. It's not that. I'm not saying that. I'm saying E changes with Z. B changes with Z. There is a huge difference between these two. Understand that. Do you understand that? Yes or no?
Like if we put it in terms of an equation, like we can write electric field vectors E naught sine omega t minus kz, and B vector is equal to B naught sine omega t minus kz. So both are varying along with z axis, but not in any other axis like that.
Yes, exactly. Yes. So let's write that down. So E equals some E naught. Instead of sine and cos, I will do e power I kx minus omega kz minus omega t. And B equals some B naught e power I kz minus omega t. Okay, is this okay now?
Electric and parallel.
Yeah.
Electric and magnetic parallel. Why, sir? It should be perpendicular. Na?
We don't know the direction. I told you there are no directions. We did not fix the direction. E naught can be perpendicular to B naught. E naught B naught. E naught B naught is 0. It can be that. We don't know that. We don't know that. This E naught can be pointing in this direction. This B naught can be pointing in this direction. We don't know that. We have not specified anything like that. We don't know that yet. Okay. Okay. Not yet. Not yet. Okay. Now let's apply div E. Div E is 0, right? We started off with this equation. Divergence of Z is 0. E is 0, right? So dou E x by dou x plus dou E y by dou y plus dou E z by dou z is 0, right?
Yes.
Yeah, but we also said E is a function of just Z. Okay, which means Ex is a function of Z, Ey is a function of Z, and Ez is a function of Z. Am I right? If Ex is a function of Z, then this term must go to 0 because Ex is not a function of X. It is a constant along X. The same thing here. Ey is not a function of Y. It is only a function of Z. So that term must go to 0. So remaining term is this. Okay, so dou Ez by dou Z is 0, which means Ez, that is the vector in the Z direction, the direction of propagation, either is a constant or a 0. The vector in the propagation direction does not change. What does that mean? The electric field vector does not change in the direction of propagation. It does not have a component along the direction of propagation. Electric field vector does not have a component in the direction.
Means it is perpendicular.
Yes, that means it's a transverse wave. It's a transverse wave. Yeah, the same thing with B, because the divergence of E is 0 and divergence of B is 0. The same thing applies for divergence of B as well. So B is also transverse. Am I right?
Yes, sir.
Yes.
So it's a transverse wave. We just derived that the electromagnetic wave is a transverse wave. Okay. Now, if you apply curl on E, okay, and curl on and differentiate B with respect to time, we know this is the equation curl of E equals minus dou B by dou T. If we do that, we will see that E and B are perpendicular to each other. We can apply curl of E here and curl of divergence of B here. We can see that they are both perpendicular to each other. E and B are perpendicular to each other. Okay, just from Maxwell's equation, we can show that. Okay, that I'll leave it to you guys. It's pretty simple. Okay, so we can visualize the wave. The wave, it's this Z direction. The wave is going like this. Okay, E is along like this direction. E is going like this. Okay, it's oscillating perpendicular to the direction of propagation, and B is perpendicular to E, so it's like this. Okay, it's moving like that, right? Right. This is how your wave equation looks like. This is how the electromagnetic wave looks like. Okay, this is E, this is B. Got it?
Yes, sir.
Okay.
Yes.
So yeah, so we have basically
Yes,
derived.
sir.
Yeah, we have basically derived the properties of electromagnetic wave. It's a transverse wave with E and B perpendicular to each other, and it's propagating in a direction perpendicular to both E and B. Right from the Maxwell's equations. Okay.
Yes.
Yeah. All right. That's pretty much it. And Maxwell's equations are it's a good starting point for electrodynamics. Okay. But electrodynamics is a really deep subject. Okay. I don't think you will. Maybe some of you might. Some of you might get into electromagnetic theory. It's a starting point. This is a starting point. This is a starting point for whole of electrodynamics, whole of optics, whole of relativity. Okay, why relativity? Because Einstein derived his relativity equations, all his relativity equations, by assuming C as a constant, because he believed in Maxwell's equations. Okay, there is no way, nothing can change the velocity of C. Okay, whether you are on a moving frame or a stationary frame. Okay, so he started from Maxwell's equations. That's how he got to relativity. Okay, so this forms the base of a whole lot of fields in physics. Okay, but here I will stop.
So there was a case in the black hole theory about the speed of light, that due to the strong gravity, there is some change in the speed of light. There was a hypothesis, not theory actually. I have read it in some paper, that they were proposing due to the very strong fluctuation in the space-time fabric, there was some change in the speed of light.
Okay, okay. There were these theories long ago. So gravitational, there were theories about there is an expansion coefficient that Einstein introduced in special relativity, and that changes, and gravitational constant changes across the space and all that. There were so many theories. One single experiment basically made all of them false. Okay, one experimental observation, and that experimental observation was done by LIGO, LIGO, Laser Interferometric Gravitational Observatory. So this is what they did. They observed somewhere about 1 billion years ago, in some point in space, they observed a black hole and a neutron star colliding. Okay, and when a black hole and a neutron star collides, it both creates a ripple in the gravitational field, which forms a gravitational wave, and that also generates a lot of X-rays, huge amount of X-rays, right? Okay, now both light and the gravitational wave travels at the same speed, exactly same speed, c. Okay, and that is because c is not, it is not related to speed of light, it is related to speed of causality in the universe. Okay, I think I told you guys about that. So you could observe this collision both in LIGO as a gravitational wave and with your X-ray telescopes like Chandra X-ray Observatory. Okay, Chandra is for Chandrasekhar. Yes, Chandrasekhar. Okay, so this observatory was also observing the same collision at the same time. And do you think what the difference? Do you know the difference between the two signals was? The signal of the gravitational wave and the signal of the X-rays. This happened a billion years ago. Okay, and the difference was 3 seconds. Okay, that was well within the experimental error. So obviously the gravitational wave and the light wave were traveling exactly at the same speed. So you cannot, there is no way that in the universe, anywhere in the universe, you go that the speed of light changes. There is no way. That cannot happen. That is not possible. Otherwise, you wouldn't observe them to be so close to each other, arriving at the same time exactly. Does it make sense?
Yes, sir. So, but it is really hard to like interpret in a physical sense, because what we have observed till now, that due to speed is a relative thing, it can be changed by changing the frame of reference and all those things. So,
well, that is the basis of relativity. The basis of relativity says that speed of light does not change, and without relativity, your GPS does not work. I think I talked about this, right? Have I?
Yes, yes.
Yeah. So so relativity is important, and relativity works. We know that it works. So obviously that means that speed of light is constant across all frames of reference. Okay, and it's not just one. This is just one instance. Okay, there are thousands of instances where relativity is known to be precise, like perihelion of Mercury. Okay, why Mercury goes around in flowers, in flower orbits. Okay, so there are thousands of experiments, literally. So there is no way that relativity can be wrong at our level of observation. Okay, of course there is going to be a quantum gravity theory, and that will modify, not disprove, modify relativity at very high energy scales and very small length scales. But our length scales and our energy scales, relativity is perfect. Okay, at very high energy scales, which is near black holes, relativity has to be modified, of course. Okay, but we don't know how to modify that yet. Okay.
Yes, sir.